we're now introducing Resonance Enhanced Force Volume, or REFV AFM-IR. Fundamentally, this is built on the main principles of Resonance Enhanced AFM-IR, where we're doing a direct excitation of our AFM cantilever while we're probing the sample surface. But by using a force volume or data cube operation method, we're avoiding the limitations of operating in contact mode. That is to say, we're reducing the lateral forces and going pixel to pixel, not scanning on the direct sample surface. This can be approximated here in this pictogram on the right-hand side, where what we see is the approach curve of the AFM probe going onto the surface, acquiring a force curve, holding at a set force for a period of time where our infrared measurement is being validated, then retracting and withdrawing where we can measure out the adhesion or other mechanical properties, and then moving to the next pixel and doing this over again. And we can operate again in these same two ways as previous, where we can do a short time frame for each pixel for imaging, where we can collect images in as little as 3 minutes, or we can hold for a longer period of time and sweep our infrared laser source to get spectra at these individual points in space. And again, we're doing all of this with the mechanical properties simultaneously. So again, on the right-hand side, we have this pictogram, but what does this practically look like? And here I have the actual measured out traces of this resonance enhanced force volume technique, wherein we can see our approach curve, the force that we hold at, the dwell time that we're holding at, and then the infrared signal that is being read out during that period of time. And then the last thing, which we'll touch on a little bit later, is the tracking of the mechanical phase of the cantilever to reduce any distortions due to mechanical artifacts. And so here we can see that that is being kept at 0, which means no mechanical artifacts in the measurement process. So now let's start to look at some data. So here is an example of our PSB PMMA core shell sample. This is a small agglomerate of block copolymer, PS and PMMA. And it forms into these little spheres that can then aggregate together. You can see here that this sample is about 200 nanometers across and maybe about 5 to 10 nanometers tall. And if we try to look at this using traditional resonance enhanced AFM-IR, we can't actually image this material. It's too loosely bound to the surface, and so you end up kicking it around like a hockey puck. Using resonance enhanced force volume AFM-IR, we're able to read out the chemical contrast we can see in the bottom right due to PMMA, and we can see the high lateral resolution that we're getting here, very much equivalent to tapping mode, which is sub 10 nanometers. In this case, at the step edge here, we can read out 6.5 nanometers of lateral resolution with resonance enhanced force volume. What's more, in addition to this, we're also reading out the mechanical properties from the force curve. So now we're able to simultaneously see this adhesion channel or the modulus channel while we're doing this measurement. So to expand the picture we were looking at earlier, we were able to now use our force volume operation with resonance enhanced mode to offer the same sub 10 nanometer spatial resolution while avoiding lateral forces, working with soft samples, and then doing new innovative ways to characterize our samples with simultaneous mechanics and the ability to sweep a frequency through the measurement. And we'll take a look at that very soon.